LangChain, Retrieval Augmented Generation. I know RAG is so 2023, but still a lot of people haven't used it or haven't used it for a while, and I'm finding an increasing number of people need it. So let me go through the basic concepts and a simple demo to show you how it's done. My name is Ken Kousen, and this is Tales from the Jar Side. What is RAG? RAG stands for Retrieval Augmented Generation, which doesn't really tell you much, but the idea is that you retrieve the relevant pieces at query time of the information that it has stored and include them in the prompt that goes to the large language model. The idea is not to have to go and include your entire document in the context window, which even if it would fit, will generally wind up using up way too many tokens. You see we have several documents here, each of varying numbers of tokens, and now that's in the old days when RAG was first developed. Context windows, the amount of tokens that a large language model could hold at any given time, were like 8K or 16K or sometimes 32K. Now they're a couple 100K or in some cases a million, but we'll come back to that issue. The idea is that you don't want to put all of your documents in there necessarily, and even if you did, then you'd have questions about how well the search capabilities would work. So here's the problem that RAG solves. Large language models have a given context window. It's the limit on how much text they can see at once, and you don't want to just paste your entire document library into there. It may not fit. So to give you a quick illustration of the RAG process, I'm going to use here a web page that comes from LangChain4j, one of the major Java frameworks for doing RAG. You really don't want to do RAG without a framework of some kind. You can do it manually, but it's a lot more work that way. We're going to look at three different options in this video. One is the regular LangChain framework in Python. The second one will be this one, LangChain4j in Java. And the third one will be Spring AI, also in Java. And by seeing what concepts are carried across all of them, you get an idea what's actually involved in the RAG process. So here from the LangChain4j documentation, they say here's what you do before you send in any queries. You take your document or documents and you run them through. First of all, what's not shown on this figure is some kind of document loader. Load the documents either from PDFs or from spreadsheets or remote URLs or whatever it might be. Then you run them through what's called a text splitter to break them into manageable chunks. The size of those chunks is one of your tunable parameters, how much overlap you include. These are all decisions you make during the process. That results in a series of what they call either chunks or segments, depending on the documentation. Then comes the interesting part. We run it through something called an embedding model to create vectors. A vector is just a series of doubles. It's a list of doubles that represent the information in some high order space. Now that sounds complicated. We'll look at that a little bit more after we've seen the overall process. Eventually, once you have those vectors, you save them in a vector database, or what they're referring to here as an embedding store. So this is a database that allows the vectors to be searched based on the magnitude and direction or all of the different dimensions associated with the vector. Then what LangChain4j documentation says is a query comes in. So when a user asks a question, they run the query through the same embedding model and come up with its vector, the vector representing the query. Then they search the embedding store, doing what's called a similarity search, to find the segments in the documentation that are closest to the query. We want to find things that are hopefully the most relevant. Then those segments are added to the query and the whole thing is sent to the large language model. So there's your basic concept. And this happens over and over again. Now here is the same thing in the Spring AI documentation. So this is a figure that's taken from there. So you see the same steps just shown a little differently. A data source goes through a reader, some kind of reader, PDF reader, Apache Tika is a popular reader. There's a lot of these things and results in these documents. Now document here is actually a technical term. It's a class in one of these APIs, but it does represent information. Then this transformer is the text splitter. They just didn't call it a splitter here. you wind up with these chunks. See, over here they called it chunks, and the other one they called them segments. And then it says you write them using a writer to the vector store, but that process again is where the embedding happens. So all the stuff in this top part of the diagram happens before you start accepting queries from users. Then when a chat request comes in with a query from a user, then we take that and convert it to, again, the appropriate vector, search the vector store. I've got a typo on the diagram, but okay. And that gives you the chunks that are associated with the information. So there's the user query. These are the chunks from your information that are closest to it. And everything is sent in the prompt to the chat model. So same basic idea. What about LangChain? The basic LangChain documentation is here. I've got some of it here. And you see their figures are much simpler, but maybe it'll show the information better. Here we load documents, let's magnify that, load documents from a variety of sources, PDFs, JSON data, URLs, tables, whatever it might be. You split them using a text splitter or some other kind of splitter into chunks. Then you run through the embedding model to create these vectors. See how they're just lists of doubles, if you will. And these are saved in the embedding store. So basic preliminary part, the part where you save your information. Then when a query comes in, there's another figure which says, okay, here's the question. And then we have a little magnifying glass, our search there, to search the embedding store for the documents inside the chunks in the embedding store that are closest as a vector to the question vector. Both of those are added to the prompt, run through the LLM, and then gives us an answer. So there's your basic idea, the basic concept of all of them. Now, what about those embeddings? Let me take a moment to explain just the basic concept of an embedding, and hopefully this will give you enough of a sense that we can go ahead and look at the code. So say we were doing a two-dimensional embedding. All our data is going to be saved in 2 dimensions. And that's not enough, but it's better for us to visualize. So here you see we have vectors. Think of a vector as going from the origin here to any of these points. So we have vectors that tend to clump together. So all the fruits tend to be in one area, this quadrant over here. All the cities tend to be in another quadrant, and my support to our friends in Minneapolis. Down here we have all the vectors representing animals, etc. So when you're doing the preliminary storage of your information, it's creating some kind of embedding vector of, I don't know, 1,500 dimensions. It's pretty high dimensional, not just 2D like this. And then they're saved into the vector database. Then the way the retrieval comes in, there's a question like, what fruits are high in vitamin C? And it should produce a vector by the same embedding that's close to the fruits, if you will. Something like that. And then they'll even have the degree of match. Now, some of these embedding mechanisms show the similarity score, which has to be high to let it know it's really close. Some of them prefer a distance score, which has to be really low to say, yeah, it's not that far away. So again, it's just confusing, but it's the same concept. It's to find the data points that are closest to our embedding vector. Okay, now let's look at code. Let's look at the project here. It's in my GitHub repository under my last name, Kousen. That's my quote organization there. And then here, the name of the project is called RAG Demo. And you will see it has, in fact, 3 different sub-projects inside it. They're not related, or I tried to keep them as independent as possible. There's one in Python, there's one that is in Java using Spring AI, and one in Java using LangChain4j. And we'll take a look at those. Now, in order to have a PDF for us to search, just to demonstrate this, you'll see that in all 3 of them, let me start with the Python one, you will see under Documents folder, there is a sample document, just called sample.pdf. And in fact, what that document is, if I was to open it up here, is you see it is the Attention is All You Need paper from, it says from the authors at Google. So we have permission to reproduce all this. And this was basically the paper that created our AI revolution with generative models that's been happening ever since. So there's the actual PDF that I'm going to search on this. So Rather than look at the information on this page, let me go to an IDE. Here is PyCharm. You can use VS Code, you could use Cursor, you could use whatever you prefer. Let me open up a terminal here, and I already have a virtual environment. You see it detected that, and then I could say, okay, let's run the main script. And now it found the PDF. In fact, you could see it here. It loaded 15 pages from that sample, split it into, as it turned out in this case, 52 chunks, and stored them all in the vector database and said, LangChain is ready. So here are some potential questions you could ask. So let me grab that first one. What is the transformer architecture as a sample? And we'll see what it comes up with. Now it takes a moment to start up and to search the vector database, but it will give us back information, hopefully from that paper. Sometimes I'm a little more specific about it. Sometimes I say using the paper provided, ... because this paper is likely in its training data anyway. But you can see it did give an answer, and along with key points and everything. Now, what's also in my demo is if you ask a question and you precede it with debug, then it will also show you which chunks match the closest. And I think I'm searching for just the top 4. So how does self-attention work, for example? So this time you could see that we got an answer back. I don't really care about the actual answer, but below it, it's showing 1, 2, 3, 4 chunks, because I limited it to that number, along with their scores here, and to try to give us an idea how accurate or how close they are based on the information. And those are okay, but good enough in our case, because it looks like we got a decent answer anyway. To show a failure mode, just to demonstrate what happens when you ask something that is not in the information. Let's see, this is being recorded in early 2026, so let me ask it, who won the 2025 World Series? And hopefully that's late enough that it's not in the training data for the underlying model that I'm using, which was GPT-5 Mini, I believe. And yeah, there we go. The provided context contains no information about that, so it doesn't. Now, to show you the Java implementations, here, for example, is the Spring AI one. And I'll go through the question and answer advisor and everything in a minute, but let me at least show you that this will in fact run. So let me run the Gradle task boot run. Here I have a little bit more debug information available so that you could see the application starting up. It found the PDF, it's processing it page by page. It's splitting up each page apparently into 2 chunks, which sounds pretty consistent with the other one as well. In this case, it mentioned the document ID for each of those chunks in case we want it. So I get to the bottom of that, and then we're back again asking a question, and this time I'll just go directly to the debug approach and say, what are the key contributions of this paper? And there you go. Again, I turned off the word wrap because I don't really care about looking at the details of the information here, but I did want to show that we did in fact retrieve multiple documents, and they all have their, in this case, distance. So if the Python one was showing a similarity between, say, 0.4 and 0.5, this is showing a distance of 0.6 to 0.7, 0.8, so it's the other direction. But still, we do get good answers out of it. Finally, showing the LangChain4j implementation, I'm using an Apache TCAP parser, file system document loader, etc. All this information is pretty well documented, etc. But let me at least run it and give you an idea that it also works. Let me do the Gradle W run task here, which should start it right up. So same information, although this one I added in a second PDF just to show that it will load all the PDFs in the documents folder if you wanted to. So it's splitting with overlap and embedding and storing. I just didn't print out all the documentation here, and now it's ready to respond to questions. So again, I'll ask a debug question. What is attention according to this paper? And once again, you see that we got information out. I'm not sure why. That looks so weird, but not our problem. It did match, and we did get a decent answer out of it, out of all that. So interesting. So no Spring Boot involved, no container, no nothing. It's pure Java. Everything's running from a main method, basically. So why show both of the Java implementations? Well, if you are a Spring person, and many people in the Java ecosystem are, then Spring AI is a project that is part of the Spring ecosystem that you could add to your existing Spring project and take advantage of. If you're not a Spring person or you don't want to use Spring AI for some reason, LangChain4j is an excellent fallback. If you are already doing your project in Python and want to stay in Python, LangChain is an excellent framework to help you work there. But most enterprise applications, which are the sorts of things I work on, tend to be written in Java on the back end. Python's great if your whole system's in Java, but if you're trying to do anything that integrates with other systems, it's a different process. Again, you can use any of them. I'm not trying to argue one is better or worse than the other, but they're all there. The flow is the same no matter what. You load the documents, you break them into chunks, you convert them into vectors that get saved in a vector store. Then when a query comes in, you convert that to a vector, look for the similar vectors in the vector store, and provide everything to the large language model to give you some answers. Okay, now taking a look at some of the details here, in the LangChain4j one, you could see I'm using a file system document loader, which has a load document method, which loads a document from the specified path. It's parsed using a document parser and returns this instance of the document class. Again, that's an actual class in LangChain4j. We're using an open source project from the Apache Software Foundation. In fact, in this case, it's the Apache Tika document parser. You can also add metadata, information about the data you're parsing. And I got to tell you, a lot of the success or failure of RAG systems comes down to figuring out what the metadata is and adding that with all of your documents. That's really helpful to the LLM when it's trying to find things that are supposed to be affiliated with it. It also helps you preserve more global context information. When you break things into chunks, you lose a lot of the surrounding information, and this will help that. Whereas in Spring AI, here is a service that I wrote that you auto wire in a vector store, and to populate the vector store, that's what this document loader service is for. It basically looks for the PDFs and it calls this load PDF on each one, which is going to use a PDF resource. So this is basically a resource in Spring IO, and I'm using a page PDF document reader. We get that, everything in Spring AI, they really like functions and suppliers and those sorts of options here. So this loads the documents, and then this apply method is going to do the splitting. See, there's the apply method on the text splitter to break it into chunks. And then down here, the add method, this adds just some metadata. The add method down here is what does the embedding. So that populates everything in the vector store. Looking at the Python code, again, we have to load and chunk the PDFs. So we find the path to the PDF and we use a PyPDF loader to load it. And then this is using a recursive character text splitter to break it into pieces. And then here in step 3 in the vector store.python, we use the OpenAI embeddings and an in-memory vector store at the moment from the documents, and that will encode everything and put it inside the vector store. Now, I'll mention it here. We don't have time to get to it in this video, but just letting you know, there's a second branch on the GitHub repository that replaces the in-memory vector store with Supabase using pgvector, the extension that goes on to Postgres. So we do have an example using the full one, but this is just to keep the code simple for the moment. In the Spring AI approach, I want to show you two things. First of all, I have a bean that creating the chat client and creating the vector store. So we auto wire in the embedding model, and in this basic example here, once again, it's an in-memory vector store, but you could use any of these, and in the other branch I'm using the PG vector store. But you're adding an advisor. Spring AI really loves this idea of little interceptors that intercept queries and do things with them. This advisor is called a question answer advisor that wraps around the vector store. If you look inside the source code for the question answer vector store, look, what you have here is the default prompt template, which is this multi-line string that says, here's the query that was submitted in text form by the user. Context information is below, surrounded by dashes. So here, this will be where the chunks go in that were found by the similarity search. And then the rest of the query says, given the context and provided history information and not prior knowledge, reply to the user comment. If the answer is not in the context, inform the user you can't answer the question. The point is, this one already has the query here to work with everything built right in it. You don't have to tell it what your query is. That's just a feature of Spring. So you can customize the prompts, you can modify any of this however you want, but you see that it does run, it runs pretty nicely. One thing I will point out about the persistent storage is that when I did run this on Supabase here, with the PG vector database, there's a little bit of configuration you have to do. You pick your database and then you tell it you want it to be a vector store. Let's take a look at the data. And you could see inside the vector store, for example, there's some auto-generated ID. And then here is the vector of embeddings. You can see there's a bunch of doubles in there that go on and on. Here's the text chunk that generated that embedding, and then whatever metadata we added. So the similarity search is taking advantage of that information. I just didn't go through the details of that code, but it's all in there. By the way, if I look at the LangChain one, here's the actual embeddings. It's slightly different. They just use different defaults here. And if I ran the Spring AI one, it would look a lot like this one. So it just depends on which embedding model you use. In each of these cases, I use the cheapest but effective, the state-of-the-art embedding model from OpenAI. In fact, here's the embedding model I use, text embedding 3 small, right on the OpenAI documentation page. All right, so now let's get into a couple more global questions. What about when your data changes frequently? You just run the RAG process over it periodically. Also, RAG is good about telling you which individual pieces of the underlying document led to the answers you saw. That's what I was showing in the embedded model. So if the cached entries become stale, then you could, if you miss them, then go ahead and see did the documents change, retrieve fresh chunks from the data store, or we could reuse them and go on. It's just basically any other caching mechanism. So let's recap. RAG lets you give a large language model access to your private training data without retraining it or anything like that. 6-step process really. You load the data, you split it into chunks, you embed the chunks into a vector database using the embedding model, so store the vectors in the vector database, and then when you retrieve one, you turn the query into a vector as well and extract the similar vectors from the vector database and send everything to the LLM. The question becomes a vector, the nearest chunks become the context, the LLM generates an answer. The code is all on GitHub, where I gave you the URL earlier. It'll also be in a link in the description of this video. Hopefully that'll help you build a working RAG system in whichever one you want. Good luck. Let me know how it works out for you, and take care, everybody.